So, have you ever really stopped to think about what hearing is? I mean, it all starts as just a pressure wave moving through the air, right? But somehow, our brain turns that into music, into speech, into the sound of a car coming down the street. In this explainer, we're going to go on this absolutely incredible journey. We're going to trace that exact path from the outside world all the way to the electrical signals our brain can finally understand.
And to really appreciate this, we're going to have to shrink ourselves down, Fantastic Voyage style, and actually ride a sound wave right into the ear. And, like the quote says, get ready because we're about to see some seriously strange and wondrous things. I mean, the biological hardware we're about to explore is so incredibly elegant, it makes our best recording technology look, well, kind of primitive. Let's dive in.
Okay, so here's our map for the whole adventure. You can see the trip is basically broken down into three main areas: the outer ear, the middle ear, and then the inner ear. That's where the real magic happens. And trust me, each stage of this journey presents its own unique puzzle that our auditory system has evolved to solve in just a brilliant way.
All right, part one of our adventure begins now. Our little sound wave is just cruising along through the air, but to get to the brain, it's got to conquer some major obstacles right at the start, in the outer and middle ear. You might think the outer ear is just a passive funnel, right? Nope, it's way smarter than that. The ear canal itself is actually a resonator. Think of it like a tiny little organ pipe that naturally boosts certain sounds, specifically frequencies between about 1,000 and 6,000 hertz. And guess what? That's the sweet spot, the most important range for understanding human speech. So right from the get-go, your ear is actively shaping the sound. So what about the fleshy part you can actually see, the pinna? Well, its job is a little more subtle than you'd think. Here's a wild piece of trivia for you. When Van Gogh famously cut his off, he didn't actually go deaf in that ear. Turns out, the pinna's main job isn't just to collect sound, it's to create these tiny little delays and echoes that help your brain figure out where a sound is coming from, especially if it's above or below you.
Okay, so we've made it past the outer ear, but now we hit the big one, the boss level, if you will. Our sound wave has been zipping through the air, no problem. But the next stop, the inner ear, it's filled with liquid. And that, my friends, is a massive problem in physics. What is the biggest challenge of getting sound to go from air into fluid?
Well, the problem has a fancy name, impedance mismatch. But forget the jargon. Just think about it like this. Have you ever tried shouting at a friend who's underwater? What happens? They barely hear you, because most of that sound just bounces right off the surface of the water. That is the exact problem our ear is facing. So, how in the world does it solve this?
The answer is just a brilliant little piece of biological engineering. The middle ear bones. They're basically a mechanical lever system. They take all the force from the big eardrum and they concentrate it onto the much, much smaller oval window of the inner ear. And by doing that, they jack up the pressure by 20 to 30 times. It's this incredible boost that's just enough to push that vibration into the fluid. Problem solved.
And just like that, we're in. We've breached the barrier. Thanks to those amazing little bones, our sound vibration is now officially inside the inner ear, in a tiny snail-shaped structure called the cochlea. This is where the real detailed analysis begins. Welcome to the Spiral Analyzer.
Now, this thing is coiled up super tight, kind of like a snail shell, just to save space. To really get what it's doing, it helps to imagine it uncoiled, like in this picture. When you do that, you see it's really just a long, tapered tube, and it's divided by this really crucial partition called the basilar membrane.
And this membrane, this is where the genius of the cochlea really shines. It's not the same all the way along. The best way to think about it is like a piano keyboard. Every single spot along its length is tuned to vibrate at one specific frequency, one specific note.
So, when a sound comes into the cochlea, it creates this traveling wave that moves along the membrane. And check this out. High-frequency sounds like a piccolo make the stiff, narrow part right at the beginning vibrate. But low-frequency sounds, like a deep bass note, they travel all the way down to the loose, wide end. The cochlea is literally creating a physical map of sound frequencies. How cool is that?
What this means is the cochlea is performing what scientists call a spectral analysis. You know how a glass prism takes white light and breaks it apart into a rainbow? The cochlea does the exact same thing, but for sound. It takes a complex sound wave, like my voice, and it mechanically deconstructs it into all of its individual, pure frequencies. It's a prism for sound.
Okay, we've reached the climax of our journey. The sound has been collected, it's been amplified, and now it's been sorted by frequency. But it's still just a mechanical vibration.
Your brain doesn't understand vibrations, it understands electricity. So now it's time for the final magical conversion, turning that vibration into a signal.
So here's the final puzzle. How does the physical movement of that membrane become an electrical signal that the brain can actually read? The answer lies with these incredibly specialized little cells called inner hair cells.
This picture shows us exactly how it works. You can see the inner hair cells are just sitting right there on the basilar membrane. So as the membrane moves up and down, it creates this shearing force that physically bends the tiny little hairs, the stereocilia on top. That physical bending, that is the trigger for everything that comes next.
And the sensitivity of this system is it's breathtaking. These little hairs only need to bend by about 0.3 nanometers to trigger the sensation of hearing. To put that into perspective, if one of these tiny hairs were as tall as the Willis Tower in Chicago, that's the same as the top of the tower moving by just 2 inches. The sensitivity is almost impossible to even comprehend.
So how does that tiny, tiny bend create a signal? It's this elegant, purely mechanical 4-step process. First, the little hairs bend over. Second, that stretch pulls on these tiny protein filaments called tip links. Third, those tip links physically yank open these little molecular trap doors on the cell. And fourth, as soon as those doors are open, bam, positively charged ions flood into the cell, changing its electrical state.
That rush of positive ions changes the hair cell's whole electrical vibe. And that change tells the cell, okay, release the messenger. It squirts out a chemical, a neurotransmitter, which then signals the auditory nerve fiber connected to it to fire an electrical spike. And just like that, a mechanical vibration has become a neural signal ready for the brain.
And there you have it. Our sound wave has completed its transformation. It's now an electrical code. So for the final leg of the journey, we have to send that message up to headquarters, the brain. And we do that through the auditory nerve.
The wire that carries this message is called a neuron. These are the fundamental building blocks of your entire nervous system. They're these amazing specialized cells that are designed for one thing: rapid communication. In this case, they're the cable carrying the sound we just processed up to the brain.
So in simple terms, one end of the neuron receives that chemical signal from the hair cell. If the signal is strong enough, the neuron fires its own electrical spike down its long wire, or axon. When it reaches the other end, the message gets passed on to the next neuron in the chain, carrying that sound information one step closer to your conscious awareness. It's like a relay race to the brain.
And with that, our journey is complete. We've followed a signal from a pressure wave in the air all the way to an electrical spike in the auditory nerve. The message has been delivered. But this, of course, leaves us with the biggest question of all, doesn't it? How does the brain take these simple electrical spikes and turn them into music and language and emotion? Well, that's a story for another explainer.